Okay, in this session, we are going to discuss some fundamentals of financial derivatives and particularly the way the stocks move. And the mathematical foundation of that, it's the so-called geometric Brownian motion, and we'll get to it at some point. First, we're going to go over how to install and compile the software required for these experiments. So go to GitHub Aquarians. So download the code. We're going to use HTTPS. So I've covered the prerequisites and how to install them in a previous tutorial. You could watch that if you don't know how to install them. Otherwise, you just have them here. So start the git bash. Have somewhere where you download the code. I have projects folder on my PC. Let's use Commander Twin Panel Explorer. So projects, git clone, and this. Okay, now start IntelliJ. And open the project. Remember where you put it. Projects and this Aquarians folder. What this is, let's take a look. Project structure. So we are using Java 1.8. Build. Yeah, we have build. And now we have to, don't forget to install the database. So we have a pgadmin. So that's the PostgreSQL database. Don't forget what password we used for the database. And here in the Java project, Control-Shift-N to look for a file and look for database.sql. So this is the file which creates the database. Take some time to start. Expand the servers, provide the password that we used. Okay, and we have a database that I've previously created. I'm just going to delete it and recreate it. Okay, so you have to create a database that you know. So remember the name. I'm calling it Aquarians. Right-click, query tool, and just copy-paste all database SQL into this window and run. This has created the database structure. Okay. And now let's create a run configuration. So run a debug configuration like this. So an application, we are going to call it backtester. Main class It's application, module 1.8, class path of module backtester, no program arguments, and this is important where the working directory should be under backtester source resources. So here, no, backtester here, apply. Now we have to verify the database connection parameter. So Control-Shift-N and look for config.properties. And here you'll see the connection parameter. So the database is called Aquarians. And the password, the use and the password, in this case, I've left them default, but you should change the database password and use whatever you think. And you can modify it here. So you can connect to it. Let me try to put something different here. So click this button to start. And nothing happened, apparently. So we can check the log, which is in backtester source main resources backtester. So we have to go there. So navigate public Aquarians backtester source main resources backtester. We have the backtester log, and we see that password authentication failed for user Postgres. So make sure that you use the right password. In this case, change it to this. Save, run again. And now it has started. We can also examine the log. Shift G, like capital G to go to the end of the file, and it has started. Okay. So we have configured the application to run. Okay. So before we start talking about the Brownian motion, let's do two things. One of them will be to import some actual real stock prices, and the other one will be to generate some theoretical stock prices according to this Brownian motion. So go to Yahoo Finance, Yahoo Finance. Okay. Let's look for, let's say, SPY, which is the Standard & Poor's ETF. And you can go here, historical data. You can choose the time period. So I'm going to choose from like 10 years. No, let's choose from 2000. From 01/01/2000 until now. Done. Apply. Download. Okay, it has downloaded. Now we have to put it in some directory where it will be recognized. I'm going to call this data. So move it from downloads, cut, paste, and we have the directory data. And now we are going to import it in our database. And how we do that, we are going to enable a job named import Yahoo stock prices job. And this job has a folder, which in our case, it's data. So copy this, put it here, use Linux style delimiters, folder delimiters, and start a log. Shift and F to automatically go to the end of the file and start. We can just stop whatever has run and now run it in import mode. Control N, import prices job, and I'm going to place a breakpoint to see what happens actually when I'm running this job. So start. It has got here. Yahoo stock price import prices is running. Now at some point it reaches here. It looks for all CSV files in that folder. It's reading line by line. If it doesn't find the underlier in the database, which is SPY, it creates it, and it's inserting price by price. So I'm just going to let it run. F9 is continue. Look here, it's importing and it has completed. And I can use this tool, like the SQL tool, to query the database. Select asterisk from underliers. I see that I have SPY with ID 1. Select asterisk from stock prices where underlier equals limit 10, first 10 records. Okay, and I see that it has imported the stock prices from Yahoo. Now I'm going to run it in graphical mode, which means just disable any sort of jobs are run as a console, so no graphical interface. So disable this and restart it in graphical mode. We have this, don't need this. This is the default layout. Open the stocks layout and look for SPY. Okay, and we see that it has imported this data from 2000 until now. Looks something like this. So this is real stock data. Now in the following, we are going to use the same job configuration to generate theoretical data. So we are going to compare the way this stuff, which looks quite random, is going to look somehow similar to the data that we generated, and we know it's random because it's theoretically random. So we have generate test data. Let's look at how it's configured. The underlayer code is test data. So like this one is SPY, this one is going to be called test data. Starts at 100. So this one started around 150 in 2000. Ours will start at 100. Different parameters, you can leave everything like this. I don't need a vol skew. I just want a flat vol and start day, where we are going to start it from 2000. And options, I'm going to start it 1 year later. And end day, what day is today? 2023, November 23. So that's about it. I've configured this. And if everything is fine, it should work. So, but okay, let's stop this and start generating. Okay, it's generating option prices now. That's not so important. Actually, options are not that important now, so I'm going to stop it. Okay, so disable the job, start it in graphical mode, and let's look at the generated data and the test data. So look at the real data, SPY, start another view, and I call it test data. Load. Well, it started at 100, and in this case, it didn't go very well. So unlike the index, it wasn't a good period. It went up for some time, a little bit, and then down. Okay, let's generate another round, which means I'll have to delete the data that exists currently. So run these two SQL commands. Let's see if we load again. There's nothing here because we deleted it. So stop it, run generation of data again, enable this, run. Okay, got it finished with stocks. Options, we are not interested, just crap. So delete this thing again. Generate. Okay. And don't forget to disable this before starting graphical mode. Okay, it started again. Let's load test data. Well, now it went better. So it's all random. This time it went up. Okay, so it looks somehow similar, but we are going to investigate how these prices are supposed to be moving. So let's go back to this equation and let's look here in generate test data job, Control N, go to this, Control F12, run, and we have generate stock prices. So this is where the magic happens. It will generate prices according to this formula. So we have a normal process which does this generate path. And this is the magic equation, which we are going to discuss in what follows. So if you just want to use it, you can use it like this, but we are going to try to understand why it's implemented like this. So I switched to a document camera, and let's discuss a bit those equations. So first, when we are looking at the stock movements, we are going to look at relative movements. So if we have stock prices S0, S1, S2, different days, what's a relative move? So the relative move from one day to the other is something like S1 minus S0 over S0. So this is the relative move, or the S0 over S0 in mathematical notation. Why we do this relative thingy? Because the stocks can have very different absolute values. So one stock, let's say SPY, can be, now it's around 400. Other stock like, let's say, British Petroleum, it's around 30. So in order to compare the movement from day to day, we are going to use something that's common between these stocks, and the relative movements we can compare. They are similar, unlike the absolute values. So for starters, we are going to use relative values. And another thing that we are going to use, we are not going to use this formula. Let's say S0 was 100, S1 was 101, and essentially we have a 1% change from one day to the next. Like, right, I mean, it's 101 minus 100 over 100, which is 1 over 100, which is 1%. But we are not going to use this formula. We are going to rather use the log returns. So we are going to use logarithm in S of S1 over S0. And why we use that? Well, first, let's try to look a bit at the actual values and see that they are very similar. So let's take a look. Online scientific calculator. This one. Yes, okay. So we have 1 over 100, which is 0.01, right, 1%. And we have logarithm of 101 over 100, which is very close to 0.01. Let's take the other case. Let's say the price went down by 1%. So we have in stocks, so we have price went from 100 to 99 over 100, we have minus 1%. How about logarithm? Logarithm of 99 over 100. Well, again, it's very close to actual percent. So for starters, they are very close, and we are going to show why this happens actually. So let me share the document camera. Okay, so like this. Okay, so let's have the function logarithm of S. So the stock is a function. What's the derived? So the derivative of logarithm of S is 1 over S, right? And then we have Taylor series expansion, which says that a function, so in general, function of a variable x is equal function at x0 plus f derived at x0 times x minus x0 plus higher derivatives. We are not interested in the higher derivatives. We are just going to use one derivative. So applied for logarithm, we have logarithm of stock price at some point, not 0. It's approximately logarithm of today's price plus what's the derived of logarithm of S? It's 1 over S. So it's 1 over S0 times S minus S0, right? So this is the formula. So we have logarithm of S minus logarithm of S0. It's approximately S, well, not S1, next S minus today's S over today's S. So we know that this thing is logarithm of S over S0, which is approximately S minus S0 over S0. So we see that actually why these formulas are very close, because logarithm of S over S0, it's an approximation of the relative change. And this is more, how should I say, it's more convenient to use in finance for different purposes, but mostly because we can chain them very well. So let's say we have stock prices like S0, S1, S2, a lot of them, Sn. Now, if you would have relative changes from one day to the next, it would be, what would be the total change from one day to the other? So say we have a sequence of prices S0, S1, S2, Sn, and we want to calculate the total return from S0 to Sn. So on first day, we had S1 minus S0 over S0, plus on the second day, we had S2 minus S1 over S1, plus on the last day, we had Sn minus Sn minus 1 over Sn. Well, this thing is very difficult to calculate because we don't have the same denominator. So instead of using this, we are going to use logarithms. So in log returns, we'll have logarithm of S1 over S0 plus logarithm of S2 over S1 plus logarithm of Sn over Sn minus 1. But we know from logarithms that this thing is equal to logarithm S1 over S0 times S2 times over S1 times S3 over S2 times Sn over Sn minus 1. And the nice thing is that this thing can be reduced, and we are left with a nice logarithm of Sn over S0. So the total return of any price trajectory is just the logarithm of the last over first, just like every day. So that's why we use logarithms. And let's go back to the geometric Brownian motion. We see here a formula, which we are actually, this is the formula that we use. So the return on each day, it's some constant multiplied by time, which is the time elapsed in a day, plus the so-called volatility, times this weird thing, which we are going to discuss some other day, so next time. But we are going to see that we have, so the price on the next day is the price of today, which means the spot on the next day is the price of the spot of today times the exponential of a mean, which is this thing, mu minus sigma squared over 2, here, multiplied by time, so how much time has passed in a day, plus sigma times, now this is the tricky thing that we'll discuss the next time. It's this vol, it's sigma, and instead of using time, we're going to use square root of time. So magic, just take it like this for now. And this is actually the solution, the closed form solution to this differential equation. So we could use this differential equation, but it wouldn't be so precise. So we'll have to have very small intervals to be accurate, and at some point it's no longer accurate. But this thing is accurate for any time interval. So that's why we use the solution and not the equation. And using this thing, we get these nice price trajectories, which should be similar to how the stock prices move in reality. So next time we are going to discuss where this thing came from. So the whole idea behind this Brownian motion, how its history, how it came into being, and what was first, was the chicken or the egg? So what was first, the theoretical Brownian motion, and then we just apply it to stocks, or stocks were first? So probably, as you can guess, before someone thought of modeling them, they just moved happily for hundreds of years, and someone eventually figured out that the way that they move behaves can be modeled theoretically as a stochastic differential equation. And we are going to take real stock prices and extract these parameters from them. So see what is this mu, the growth rate, which is similar to an interest rate, and what is this sigma, which is the volatility and is the most important parameter when you price derivatives. So thank you for listening and see you next time.